Now, we have discussed the amazing nature of the semiconductor and the amazing invention called a transistor switch. Now, the manufacturing process for planar VLSI is equally impressive. And when you make chips, you're like printing money with sand. And let me explain to you why. This is the third part of our series. We're talking about chip industry overview, the race to print money. Now, we discussed that silicon is formed from the most abundant material on Earth, sand. From sand, you can purify silicon, form crystalline silicon, and then dice them into wafers. The business of printing money utilizes several different classes of manufacturing techniques. For example, wafer preparation. For example, pattern transfer using light. This is called photolithography. You have the process of doping, which introduces dopants, impurities, into the silicon to change its conductivity. There are deposition processes where materials are placed on the wafer surface, and there are etching processes where materials are removed selectively. And then there's packaging. After the devices are made, they can be packaged in a chip for use. Let me explain to you the photolithography process. In a photolithography process, for example, if we want to pattern very fine features in the metal on the substrate, you can deposit a layer of photosensitive material called a photoresist. And this photoresist is then exposed by a light that is energetic enough to cleave some of the bonds. And we use a mask material. The mask is able to selectively block the light. So in the regions that are exposed by light, for example, the material is weaker, and in the developing solution, it can be removed. So this allows the transfer of patterns on a mask to patterns in photoresist. The photoresist is then used in turn as a mask to etch the metal. After the metal is etched, you can remove the photoresist, and this is how one transfers the pattern from the mask or design to the substrate. It is similar to photography, except here the analogy of a film is this wafer. You're taking a picture of the mask through a uh, lens, through a zoom lens, and causing very fine features to be made on the substrate surface. Here is a simplified process flow for making a MOS transistor. It consists of several different stages of photolithography and deposition of materials and removal of materials. For example, we start with a silicon wafer and cover it with a oxide material by growing thermal oxide. And this is followed by photolithography, this orange layer. The resist is allowing the transfer of patterns into oxide. The resist is removed, and the oxide can be used for uh, doping. We selectively deposit a layer of dopant, and after exposing this wafer to a certain temperature, the dopant would enter the source and drain region. Then we remove the dopant, but not the oxide layer. Then we remove the oxide layer and pattern it with another layer of insulating material, in this case, the gate oxide. This is covered by another layer of photoresist. The layer of photoresist is used to pattern the oxide material. Then we grow a very thin selective layer of high quality oxide. After that, we deposit a metal layer, and this again is patterned by yet another layer of photoresist. And after that, we cover it with another layer of photoresist and pattern it again. This time we form the gate metal. And after this, you can place metal layer on top and then pattern the source and drain and gate. So you form the metal oxide semiconductor. This basically illustrates the sequential process of using deposition, etching, and photolithography to form a coplanar device. This diagram shows only the process to form a single MOS transistor, but you can use this to form billions of transistors at the same time. These are pictures of wafers held by operators. You can see that the size of wafers are different, and on it you can see repeated patterns. Each pattern is created by a step and repeat action of the photolithography process. And each one of this repeatable unit is called a die. This die is a basic unit of circuitry. This is a picture of a die after it has been diced off the silicon wafer. And this die is in turn placed into a package. This package can be handled somewhat roughly by an electrical engineer to make different kinds of circuits. So the people who are in making the circuit does not need to touch the silicon part. You cannot touch the silicon part because the surface has to be kept rather pristine. Overall, the microfabrication process involves repeated patterning, deposition, and material removal. So you rinse and repeat this many times to form structures, not only integrated circuits, MOS transistors, but also MEMS devices. Here is a picture of a smaller wafer. This is a 4-inch wafer with only 2 by 2, 4 dies. Each die can consist of many devices, and those are smaller features on a die. This die is packaged. Packaging means securing this device mechanically and have a stable environment, and also connecting the circuit to an outside pin. This socket structure allows the chip to be addressed electrically. The old way of packaging involves putting the silicon in a package. The package is coated with plastic material and therefore very secure. And each individual package can be soldered on PC board and so on. Newer technologies actually have fancier packaging. Many different chips can be packaged on chips, and these chips can form the silicon SOI or SoC, silicon system on chip. This has many more pins than the traditional integrated circuits because there are many addressable electrical nodes. Intel and other companies like TSMC, they are advancing SoC chiplet architecture. Modern chips may consist of many different chips together, built in a kind of like a Lego block. There's different tiles, SoC tile, compute tile, IO tile, filler tile, each one made on a different wafer and cut off as an individual die. Those dies are flipped and they bonded together. Here is a picture and a diagram. You can see that many layers of this silicon dies are connected by bumps, by interconnect and via structure. And this uh, SoC structure may contain memory chips, logic chips, power handling chips, and they are bonded on a circuit board. The structures are quite sophisticated. These boards nowadays are packaged into a phone. So in a phone, for example, you can see many of these chips that are uh, placed on a motherboard and then flipped again and packaged together uh, into a mobile phone. On another level, those chips can be stacked into bigger uh, cloud servers. This is an AI cloud server that uses many circuit boards containing many uh, chips. In a modern manufacturing process of a modern circuit, the process is repeated many, many times. You go from furnace to bake to alignment, inspection, eye implantation, etching, material deposition, and so on. You can go back and forth and back and forth and back and forth. Um, this one, for example, is just a schematic illustration showing that you can have 92 steps before completing the circuit processing. The process steps by modern technology nodes from 90 nanometers, 60, 40, 20, 10 nanometers, all the way to 5 nanometers. 5 nanometer nodes can go to as many as 2,500, definitely more than 2,000 steps of processing in a cycle. The leader of technology today, TSMC, Taiwan Semiconductor Manufacturing Corp, they have a process, for example, called CoWoS, chip on wafer on substrate. Chips on a wafer and on a substrate. This one is the PC board substrate. But chips are stacked on chips and then stacked on substrates. And for each die, each connection, there are dedicated manufacturers who are specializing in every aspect of it. This forms a giant ecosystem of manufacturing technology. Even the PC board today, a PC board used to be just 2 or 3 layers. Now even PC board have 20 to 40 levels with 10 micron resolutions. So everything is getting small, not only on the silicon level, not only on the package level, but also on the PC board level. So all this uh, intricate packaging and integration forms the foundation of today's very competitive semiconductor manufacturing. This is how people print money with sand. Uh, of course, you have to spend a lot of money in order to print money and have enough of a moat so other people cannot take over.